Welcome to Fundamentals of Biomolecules. Today, we are diving into the fascinating world of enzyme regulation. We will explore how our cells act like highly efficient factories, perfectly balancing their resources to keep us alive and healthy. This topic is foundational for understanding how life sustains itself under constantly changing conditions. To understand why this concept matters so much, imagine a massive car factory with thousands of machines working on an assembly line. If the machines never stop producing cars when there is no demand, the parking lot overflows and the company wastes a tremendous amount of money and resources. In our bodies, cells are exactly like these factories, and enzymes are the hardworking machines. If enzymes worked at maximum speed all the time, our cells would exhaust their energy and build up too much of certain products. Therefore, the cell needs a management system to turn these enzyme machines on and off. Now that we understand why regulation is needed, let us look at how the cell actually does it. The cell does not destroy the enzyme. Instead, it temporarily alters its shape or chemical state. One primary method is allosteric regulation, where specific molecules bind to a site other than the active site, causing a shape change that boosts or reduces activity. Another method is covalent modification, which involves attaching a chemical group, like a phosphate, directly to the enzyme to flip it into an active or inactive state. Building on those reversible methods we just discussed, there is also a permanent way to activate enzymes. This mechanism is called proteolytic cleavage. Unlike the previous mechanisms, which can be undone, this is a strict one-way process. A piece of an inactive enzyme is literally cut off by another molecule to activate it. Once that piece is removed, the enzyme is permanently turned on. Together, all these mechanisms ensure that metabolic pathways are perfectly synchronized with the physiological needs of the organism at any given moment. So, why does this precise control matter in real life? Without enzyme regulation, biological chaos would ensue. For example, if glucose-breaking enzymes never turned off, blood sugar would plummet to fatal levels. In modern medicine, many life-saving drugs work by artificially regulating enzymes. Statin medications, for instance, lower cholesterol by inhibiting a key enzyme in its production pathway. Understanding this also allows scientists to engineer microbes for producing biofuels efficiently without shutting down their own metabolism. This brings us to the mathematical side of things. Unlike simple enzymes, allosteric enzymes often show an S-shaped curve, described by the Hill equation. Let us break down the formula. V0 is the initial velocity of the reaction. Vmax is the maximum possible speed when all active sites are saturated. S, in brackets, is the substrate concentration. The exponent N is the Hill coefficient, representing cooperativity, how binding one molecule makes the next one easier to bind. Finally, K0.5 is the substrate concentration needed to reach exactly half of the maximum speed. An activator decreases this K value, while an inhibitor increases it. Before we move on, let us see this with a concrete example. We have an allosteric enzyme with a maximum velocity of 100, a Hill coefficient of 2, and a substrate concentration of 2. In its normal state, the K0.5 is 4. We want to find the baseline initial velocity. We substitute these values into the Hill equation. The numerator becomes 100 times 4, which is 400. The denominator becomes 16 plus 4, which is 20. Dividing 400 by 20 gives us a baseline velocity of 20 micromoles per minute. Now that we have the baseline, let us see what happens when an allosteric activator binds. The activator changes the enzyme's shape, lowering the K0.5 value from 4 to 2. We keep all other variables identical and plug the new K value into our equation. The numerator is still 400, but the denominator is now 4 plus 4, which is 8. Dividing 400 by 8 gives us a new velocity of 50 micromoles per minute. The activator made the enzyme 2.5 times faster instantly, without the cell needing to build new enzymes. This incredible ability to adjust speed leads us to a specific regulatory strategy called feedback inhibition. In a metabolic pathway, a substrate is converted through multiple steps into a final product. Sometimes that final product acts as an allosteric inhibitor for the very first enzyme in the pathway. When the cell has enough of the product, it acts like a brake pedal, stopping its own production. This brilliantly prevents the cell from wasting energy and resources making more of a product it already has in abundance. Let us calculate how this feedback inhibition looks mathematically. Imagine enzyme A has a maximum velocity of 120, a Hill coefficient of 1, and a constant substrate concentration of 1. Normally, its K0.5 is 1. Plugging these into our simplified Hill equation, the numerator is 120 and the denominator is 2. This gives an initial velocity of 60 units. At this rate, the pathway is happily producing the final product at a steady, healthy pace. Now, suppose the final product Z suddenly spikes. It binds to enzyme A, making it harder for the substrate to bind. This raises the K0.5 value to 5. We substitute this new value into the equation. The numerator remains 120, but the denominator is now 5 plus 1, which is 6. Dividing 120 by 6 gives a reduced velocity of 20 units. The velocity dropped drastically from 60 to 20, perfectly demonstrating how the cell hits the brakes when it has enough product. To visualize everything we just calculated, let us look at this kinetics graph. The horizontal axis is substrate concentration, and the vertical axis is initial velocity. The solid black S-shaped curve shows the normal enzyme. Notice the dashed line at 50% of maximum velocity. Dropping down from there gives us the normal K0.5. When an activator binds, the curve shifts left, shown in green. The enzyme reaches half maximum speed at a much lower substrate concentration. Conversely, the red dotted curve shifts right for an inhibitor, requiring much more substrate to reach the same speed. We have covered a lot of ground today, so let us summarize the key takeaways. Enzyme regulation is the ultimate control system of the living cell, allowing it to dynamically adjust metabolic pathways in real time. Through mechanisms like allosteric binding, covalent modification, and feedback inhibition, cells ensure that resources are conserved and toxic buildups are avoided. We also saw how the Hill equation perfectly models these changes mathematically. Understanding these principles helps us appreciate the incredible self-regulating machinery that makes life possible.